Swayam Prabha. Digital India. Educated India.
So we are looking at the virtual work. What is the principle and how we can apply it for the last couple of classes. So we have done one problem also towards the end. An example. Yeah, this was the example which we have done. And the degree of freedom which we have taken is theta here. So theta is the one which can represent everything. There are many other things also, not only theta, maybe this angle phi. So this also can be a degree of freedom, or even the distance x. So that also can be a parameter by which you can describe the position or the geometric position of the linkage. Now let's slightly move into another problem, which is definitely of interest, is the double pendulum. And so there are AB is one link and BC is the other link. And for simplicity, let's assume that there is a mass is completely distributed. The mass here is G1. This is the center of gravity. So for simplicity, what we do is that we assume that the whole mass is concentrated at its own center of gravity. And so there's a W1 and W2. And now, so this is acted upon by a force here, F. So under the action of this W1 and W2 and F, so we would like to find out its equilibrium. So the equilibrium is described, the geometric position of this is described by two angular coordinates, theta1 and theta2. That's convenient to us. But as I said, there are many other ways of doing this also. in the sense that you can also say this as x1 and this is x2. So that is also, so there are several ways of degrees of freedom. To describe the system. Can be theta 1, theta 2, or x1, x2, or any combination. So any combination, whatever combination you take, so two quantities are enough to describe the kinematics of these things. And so either theta 1, theta 2, or x1, x2, any one of that is fine for us. But however, these theta 1, theta 2 is more convenient for this one. So as far as our principle is concerned, so when this system is under equilibrium, let's assume that say maybe theta 1 is 30 degrees, theta 2 is 40 degrees, and a certain force is given with a W1, W2. So that is the equilibrium position of that. So at that equilibrium position, if you disturb it, if you give a small virtual displacement, then the virtual work, the work done by all the system of forces here will be 0. So there are three forces. So for example, if you can give it the various virtual displacements, virtual displacements can be, so let us say this is the equilibrium. So this can be anything like this, or so if this is the equilibrium position, so we are going to disturb it by delta theta 1 or delta theta 2. Or any combination of that. So the one thing which we have to so for any virtual displacement here, it can be like this, it can be like this, a little bit this way, it can be like this, a little bit this way. So for all those, that's the statement says that for any or all virtual displacements, the work done is 0. So that means that this is the equilibrium position, either this way, this way, this way, this way. For all possibilities, it should be having a 0 virtual work. So the degrees of freedom will come into the picture. So to describe so many types of virtual displacements, it is impossible. It's not possible for every plus 1 degree, minus 2 degree, plus 2 degrees, minus 1 degree. So for in any case, what we say is that a theta 1, theta 2, a small perturbation in delta theta 1, and a small perturbation in theta 2, delta theta 2. So if you can say that, so for any delta theta 1 and for any delta theta 2, if we can show for any delta theta 1 and delta theta 2, the virtual work the corresponding virtual work is 0. So that means that it's possible for any combination also it is going to have a 0 virtual work. So that will give us conditions for equilibrium. So let's analyze this system. So let us see, a little manipulations are there, not too difficult. So let us just magnify that a little bit. So what we require here is that the W1 is acting downwards. So this is theta 1, theta 2. So we are asked to find out what are the values of this theta 1, theta 2, so that this is under equilibrium. So assuming that it is theta 1, theta 2 is there, then so the, let's say, so what we need here, what we need is that W1 and W2 are acting downwards. So that means that we need, say this is Y1, so this is Y2, so the distance from here to here is Y1 and this is Y2 up to G2, and then we have X measuring from here. So we have taken these coordinates in such a manner that any perturbation here, either in 1, will give you a work done by this one, because there's no horizontal component. So what all, it may be moving, but we are concerned only how much it has moved vertically. So like this, so what will work? So what will work here is given by what? So W1 into delta Y1 and W2 into delta Y2 and F into delta X. So there are so many small new perturbations which we are introducing. Though we said that theta 1 and theta 2 are the basic angular displacements which describe the system, but we need to bring in these things to start with, and we'll slowly convert all these things into theta 1 and theta 2. So this is what the work, and this is supposed to be 0. So at equilibrium, okay. So now what we need to convert all these things. So for that, a little bit of manipulation. So let's assume that all these links are L and L. So Y1 is L by 2 cos theta, and Y2 is theta 1, and so this is L cos theta 1 plus L by 2 cos theta 2, and X is L sin theta 1 . Okay, so that's how we, so this is L by 2 cos theta 1 and L by 2 cos theta 2, and this is how we can relate thetas and with Y. So if you want to plug these things into this one, so we need a small perturbations in Y1. So it follows the same kind of differential calculus. So what we need here is that, say delta Y1, we want to convert everything into theta 1 and theta 2. So there is a differentiation of this one. So it's minus L by 2 sin theta 1 delta theta 1, and delta Y2 similarly is minus L sin theta 1 delta theta 1 minus by 2 sin theta 2 delta theta. Okay, and then we have perturbation in X, vertical displacement is L cos theta 1 delta theta 1, L cos theta 2. So everything we are trying to put it, see all these three, we want to put it in common two displacements, because though we are putting three quantities here, essentially it is only two. we have to convert that. Okay, substituting that into the basic equation. So the work is now W1 into minus L by 2 sine theta 1 plus W2 delta by 2. So it's minus LC sine theta 1 and L by 2 sine theta 2 plus F into delta X. So it's so this is what is supposed to go to 0, all the summations. So we can collect the delta theta 1 here minus W by L by 2 sine theta 1 and here minus W2 L sine theta 1 delta theta 1 and we have here and that's about delta theta 1 and delta theta 2 we have W2 2 here minus L by 2 and here plus Fn. So this is what is supposed to go to 0. So this is a one equation, right, for the work done. So this is work done by a perturbation in theta 1 and giving a small displacements in theta 2. These are virtual displacements. So here comes our principle of virtual work. So now this expression is only one for work done, but it's actually two equations. Why? It's because this has to go to 0 for any or all displacements, all virtual displacements. For example, so I can perturb theta 1 and leave alone theta 2 constant, or I can keep theta 1 constant, leave alone theta, give a perturbation theta 2. So any one of these is possible. So it's not necessary that I have to give this one and this is equal to 1. No, not at all. So this equation in work done is actually, so since this is true for all combinations of delta theta 1, true for any combination of theta 1, delta theta 1 and delta theta 2. So therefore, what we have is that we have two equations. So which is the first one in the bracket. So it's minus WL by 2 sine theta 1 that's the one equation, and the second equation here W2 L by 2 sine theta 2 as well. So these are two equations which we are getting it here, right? So so these equations you can solve, and you can solve for theta 1 and theta 2. So solving for theta 1 and theta 2, we get tan theta 1 is equal to, for the first equation, W1 L by 2 So we get tan theta 2 . Okay, so this is so thus we are able to solve for theta 1 and theta 2 by this application of principle of virtual work. Okay, so what is the beauty of this procedure is that there are two things. The beauty of this is that it is the virtual work equation will involve only those forces which will do the work, and they call it as active forces. So there are so many other forces here. There are forces here, the reactions. There are sometimes either from the floor or even from the roof. There are so many forces which are there, which will not do any work. They are reactions quite often. Okay, and then there may be other forces. So there is a combination of all these things. So for example, there is a moment. So if you have a moment, then if you have forces, so the work done will take care of all of them in a very nice manner. So moment multiplied by change in the angle, and force multiplied by change in displacements will give you the force. So that is the main advantage. So if you want to get a relationship between the active forces, the principle of virtual work is a very powerful principle. And what is the other advantage? This is okay. The other advantage here is that the degrees of freedom which we take here are not necessarily always x, y, z, or maybe zeta and so on. So it's not necessarily always the kind of Cartesian coordinate system. Here we can take degrees of freedom, anything, even theta 1, theta 2 are good enough for us. So the degrees, so the advantage here are those two advantages. One is this consists of only those forces which are active, which will do the work. And if you want a relationship between those forces, you can do it here. On the other hand, the problem can be posed in a very generalized manner. So the work, everything can be expressed in terms of very generalized degrees of freedom, as long as you realize what are the degrees of freedom, what are the convenient degrees of freedom. Here we took the convenient degrees of freedom are theta 1 and theta 2. So we are here, if you look here, so that means that these are the degrees of freedom, and we are perturbing these degrees of freedom. So if this work has to be 0, okay, for all delta theta 1, delta theta 2, so this is 0 and this is 0, so it gives you two equations. So that is also is a very powerful thing which you need to observe, is that now the work done here, virtual work done, is only one expression. It is equivalent to two equations if you have 2 degrees of freedom. If you have 1 degree of freedom, you will get only one equation. Tomorrow, if you have a triple pendulum, okay, so you have one pendulum followed by another link, followed by another link. So if you want to do that, so you can definitely have one virtual work expression which leads to 3 equilibrium equations. Okay, so that way this is a very, very powerful principle. And let's move on. So the degrees of freedom can be increased, and only thing is that this will not give an equation of non-active forces. So this will give you the equations for only those force components which will do the work. If you are interested in finding out the reactions, right? If you are interested in finding out the reactions, then what you do is that you get these expressions, then you can go back to your application of your free body diagrams. Okay, draw a free body diagram, separate diagram, and then try to solve for the unknown reactions. Okay, so this virtual work principle, not only you just see it in the case of statics, but you will find out, why don't we take work of moment? Oh, work of moment, here we don't have any moments, right? So this in this particular problem, we didn't take We didn't have any application. Somebody was asking, why don't we take the work of moment? So where is the moment here? There is no moment, right? So we are looking at the forces W1 and W2 and F, and we try to calculate what is the contribution of the work when there is a small perturbation of theta 1 and theta 2. And then we add up and then we proceed. Okay. So the one you are talking about, the moment, probably is about the problem which we have done yesterday. I mean, the last class, where we have taken an application of so if you recall, so probably if you are talking about this problem, yes, we do. Here, so this is a crank and a connecting rod and a piston here. This may be acted upon by the weights, but you can also put a weight here if you want. Okay, or anywhere. So these are three external forces, and in the sense that including moment as an external force here. And then if you represent this as theta, then a small virtual moment of this degree of freedom, delta theta, definitely will cause work contribution by m. So in fact here the work contribution is m into delta theta, right? And leave this alone. So this was a problem which we did last time, okay? And f into delta x. So here, if you just take the moment, if you take the wave force, and then the total work contributed, the virtual work expression will have ml delta theta, f delta x. And here we have introduced delta theta and delta x, but however, one of it can be expressed in terms of the other, right? So one expression, so for example, this x here, x is, so if this is r and this is l and this is phi, so it is r cos theta. I think you work it out. Last time I did l cos phi. And of course, we have introduced a phi here. And then phi is what? The expression for phi equation. So it is L sine theta is the same, sorry, R sine theta is L. So these are the three equations, basic equations that are involved. So using this, so you can get delta x. I hope you have that. This is what I did towards the end of last class. So this is the work expression. So here, instead of x, so what we converted into theta and phi, and using this, so we can r cos theta, delta theta, and all phi. So using these two equations, okay, using these two equations, I'm sorry, here, sorry, it's fine. So using these two equations, remove this delta phi in terms of delta theta, and you can take delta theta out, and then there is an expression here in the bracket which has to be 0 for all possible angles, right? So because that delta theta is out, so whatever be the delta theta, if it has to be 0, the one in the bracket has to be 0, just like whatever we have done here. Okay. So I hope this answers your. So if there is an application of m as an external moment, so then we definitely need to take the contribution of m towards the virtual work. Additions which we have to do here, I won't call modification. So here, if there is a spring included, an elastic spring, as a part of system. This is important. So all the time we have taken these links are all rigid, but look at the application here. Let's assume that this system has so the spring has a natural length, say L naught. So what we have here, let's assume that this distance is y. So we have introduced many things here. Is theta is this angle, this is a diamond. Let's assume that all lengths are same. Okay. So now there is a spring attached with some natural length L naught, can be anything. And then there's a force F applied here. Depending upon this force F, obviously this theta will depend on that. So now here, this is also a 1 degree of freedom of system. Degrees is only one, either theta or x or y. Any one of it can be good enough to be a degree of freedom. So let us see how we solve here. So here, these are 4 rigid links, but then there is one link here, which is a spring, which is elastic in nature. It's deformable. Okay, so if you want to apply this principle of virtual work to this system, so what we need here is the principle is slightly modified, which says now that, so once you have an application of F, so then this also gets deformed. You know that when it gets deformed, there is either the force is generated, or we can even say that this spring is a conservative system. So there is a certain elastic energy or potential energy increases in the spring. So spring is here. Spring is a conservative force, conservative element, in the sense that the force can be derived from its potential energy function, half kx square, or the force is kx. So that way, whatever the work done externally. So what is that here? So if you look at this ABCD links, so whatever you apply here, a small perturbation in x will cause a change in the length of the spring. So if you have a change in the length of the spring, so there will be a change in the potential energy, right? So F is non-conservative, so because it cannot be derived from any potential energy function. But however, the spring forces can be derived from its potential function of kx square, and so this is conservative. So if you have elements, and in fact, even if you think that this is in a gravitational field with weights, so then weights also can be considered as conservative forces. Okay, that's also is fine. But anyway, let's just look at this one. So if you have this kind of system, So the principle now gets slightly modified. The virtual work done by all external forces okay. So if you want the kind of force F here, so sometimes we can even say non-conservative. Okay, is on a mechanical system. Well, all these things will follow qualifiers at equilibrium. Equals corresponding change in the potential energy. So here you can write those of either the springs or gravitational force or any other. There's one more at the end. There's always a qualifier which says that this the virtual work is done by the virtual displacements, okay, consistent with the constraints of the system. Okay, so here, so we have this force here, which is non-conservative, so it's a work done we take into consideration, and then there is an increase in the potential energy of the spring. So that means that now the principle is, say if there is a, so delta U is the virtual work of say F, and there is a change in the potential energy V, okay, potential energy change. And so what we say here is that, so delta U is delta V, okay. So this is now a modification to the original virtual work principle, okay. So delta U into is equal to delta V. So how do we apply this to this this example which we have here? It's simple. So what is that which we have here is that the virtual work is F times, let us say this is X, and what about change in potential energy? So V is half, potential energy is half K. Here we write it as Y minus naught square, right? Okay, so this is the potential energy. So change in the potential energy is half, half gets cancelled, and this K the Y. Do you agree? So this is the potential energy in the spring, and then change in the potential energy we can write it as K into Y minus L naught times delta Y. Okay, so now the principle is according to the principle is F delta X plus K into Y minus L naught. Okay, so quickly you know how to do it. So you have to convert one of it into the other, or we can even convert that into, for example, you can convert Y or everything into this thing. So for example, if this is L, so we know that Y by 2 is L times sine theta, and X by 2 is L cos theta, right? So you can take it, so delta Y here, 2 into L cos theta, delta theta, and delta X here is 2L. So everything we're trying to put it in one form. Okay, so if you do that, then coming back here, so we have F into 2L sine theta, delta theta, plus K into Y minus L delta Y is 2L cos theta. Okay, so this is the expression. You can take delta theta out, and Y you can substitute back here, 2L sine theta. So then you have a relationship between F and theta, right? So you can have an expression between F, and obviously it depends upon the natural length of the spring. Okay, so thus we have really, yeah, thus we can extend our principle of virtual work to a system which consists of some members where the elastic energy can be stored. Okay, interestingly, this, so let's consider a little bit of classification. So let's say if all the forces are only conservative. So that means that there is no other types of forces. So what all we have is delta V is 0. So that means that at equilibrium, the potential energy change for any displacement. So what we can also say here, this is also equivalent to, say, maybe a dV by, if you have a x is the degree of freedom, so xi. So that means that at equilibrium, so the potential energy change for any small change in the degrees of freedom will be equal to 0. So there is also another offshoot of this one. So this is at equilibrium. So we also have another, is that the potential energy has to be stationary according to this one, but is it following a minimum potential energy, or is it having a potential energy maximum? So that is what classifies them as a stable equilibrium or unstable equilibrium. So if the potential energy is the minimum, then we call it as stable equilibrium. And if the potential, if the potential energy has a curve where it is reaching a maximum, after that it's falling, so that way we also classify. So where we can so that means that if you want to have a minimum potential energy, so this corresponds to minimum potential energy. So which corresponds to a stable equilibrium. And on the other hand, this corresponds to a point where you have the maximum point. So this corresponds to an unstable equilibrium. So that's how we can, so the principle of virtual work really gave a lot of insight into the state of the equilibrium, whether it is stable or unstable. And also it gave us a very powerful, very powerful way of handling these equilibrium equations. Because particularly in this case, if you can mix up a theta and x and y, so if you have a 3 degrees of freedom, you can take theta as 1 degree of freedom, x as another degree of freedom, phi as another degree of freedom. So you can combine all of them and get the equilibrium equation. So it's always not necessary you have to have a Cartesian system. I suppose we'll stop here. Okay.